So let's take a look at our three basic thermodynamic calculations for this chemical reaction based on data provided from our standard thermodynamic tables that we find in the appendix of our textbook. So we have in this case the combination reaction of acetylene and two molecules of diatomic hydrogen making a molecule of ethane. And as we should always do when we're thinking in terms of energy and thermodynamics in a reaction, just simply look at the reaction, the number of molecules involved, their species, and what states of matter they're in. And we can predict a lot of the time whether the entropy of that system is going to go up or down. We can assume it's going to go down because three gas molecules are going to combine into one. So rather than distributing matter and energy further, we're concentrating it. And so when we do our sum of products minus reactions for our entropy calculation, we find indeed that's the case. We have a negative entropy. Entropy is going down. Energy is not being further distributed. It's being concentrated. So we look at these data tables. This, of course, is in joules per mole as opposed to kilojoules per mole, which we have in the Gibbs calculation. We have our product entropy of our ethane subtracted by the entropy of acetylene and two molecules of diatomic hydrogen and their entropy. So in this case, we have a negative entropy, and so we are moving towards more order, okay? So that's not a driver of spontaneity generally, but we can contrast that with the exothermic change in this reaction by looking at the standard enthalpies. And we take the standard enthalpies of our product of ethane minus the enthalpies of our reactants acetylene and hydrogen, and remembering that elemental forms always have standard enthalpies of formation of 0, and we have an exothermic reaction. It's a negative H. So we have the change in enthalpy that is actually driving towards spontaneity. But is it enough to overcome the negative entropy of the delta S? So there's a general rule of thumb here, and it has to be extremely general and vague, is that at higher temperatures, the reaction will be spontaneous, but at low temperatures it won't. It's really not that helpful of a rule of thumb. I mean, it sort of is, but what's a high temperature or low is extremely relative based on the substance. A lot of things that are gases at room temperature, well, room temperature 298 degrees Kelvin, that's high in the world of a lot of gases, but something like, say, an ionic compound or a metal, that may not be that high. So it's just, you have to think of it in terms of the entire span of temperatures for that particular substance. You really can't draw a generalized rule across all substances. But in this case, yes, if we take our reaction and apply the delta H minus the temperature times its entropy change, which is what we plugged in here, by converting the joules to kilojoules per mole, so everything's thought of in terms of kilojoules, yes, we have a spontaneous reaction of 242.1 kilojoules per mole of Gibbs available energy to do work in this reaction. So in this case, the temperature was high enough for spontaneity that we were able to have an exothermic reaction that is somewhat contrasted by a reduction in entropy, and it is still spontaneous. Of course, if we dropped the temperature significantly in this reaction, we may not have a spontaneous reaction. But in this case, standard conditions of 25 degrees Celsius to 198 Kelvin at 1 atmosphere of pressure was enough to do so. Once again, whenever we see that not symbol in this type of analysis, we are assuming these conditions. This table, this information would not apply if we deviated significantly from either 1 atmosphere of pressure or 298 Kelvin. A lot of the time we will be staying at that sort of room temperature and pressure assumption. We will get later into a few situations where we aren't, but for the most part we will. So at any rate, we have our 3 analyses here. And also don't forget that if I had provided you with the Gibbs values for these substances, we could have just simply done products minus reactants for those, and I'll probably put up a video of that, but you get the idea. For delta H, delta S, and delta G, if the standard values are provided in your table, it's just simply a sum of products minus sum of reactants.